Electricity is one of our most faithful servants. It gives us light. It starts our cars, has unlimited in aviation, circles the globe with entertainment. It cooks and refrigerates our food. These represent few of the innumerable applications of electricity. Electricity at work. But what is electricity, and where does it come from? To answer these questions, let's look in on the world of electrons. The entire universe is composed of matter. A basic concept of the structure of matter is essential for the understanding of electricity, because the very force that holds matter together has an electrical nature. There are many different substances, each a combination of some of the 92 known chemical elements. Just as yeast, flour, salt, sugar, and shortening are the ingredients used in making bread, so are the 92 elements the ingredients of all matter. And if one of these elements is reduced to its purest, final form, its smallest unit would be an atom. No one has ever seen inside an atom. However, we think of it as a system of electrons circulating around a heavy nucleus at almost inconceivable speeds. In order to explain the principles with which we are concerned in this story, let's assume that we can stop the action within the atom. And further, let's acknowledge that this is a symbol representing the atom and not an attempt to show it as it actually is. It is impossible to show the correct relative proportions of an atom on this screen. For example, if an atom could be as large as the United States, one of its electrons would be only about 100 feet across. Therefore, to tell our story, we must resort to a symbol. Then we can think of the atom as being a group of relatively light, small particles arranged around a heavy nucleus. These are particles of electric energy. The lighter ones, the electrons, are negative electric charges. And the heavier one, the nucleus, carries positive charges. Normally, a state of balance is maintained within the atom by a positive charge in the nucleus equal to the total negative charge of the electrons. And when the atom contains its normal number of electrons, it is said to be in electrical balance, to be in a neutral electrical condition. It is possible, however, to disturb this normal balance, whereupon the unbalanced atom assumes an electric charge. Too many electrons will produce a negative charge. Too few will throw the balance onto the positive side. In order to visualize better the effect of this, let's introduce a color code in which the positive charge, or an absence of electrons, is represented with red, and the negative charge, a predominance of electrons, with blue. Then an object that is in electrical balance will be purple, an equal part of each of the positive and negative charges. We have been concerned so far with the electrons within individual atoms. Now let's see what happens when two or more neutral atoms come together. The outside electrons will no longer move exclusively within their original atoms, but will circulate about both atoms at once. And if we bring many such atoms close together, as in a piece of metal, then many electrons detach themselves from their original atoms and move freely throughout the metal. As long as the metal has its normal number of electrons, it is electrically neutral. But like an individual atom, it can lose some of its electrons and become positively charged, or it can pick up more than its normal number of electrons to become negatively charged. The electrons always try to get from a negatively charged body to one that is positively charged in relation to it. And if they're brought together, the electrons will flow from one to the other until both objects are equally charged. The establishment of unbalanced charges in matter is, in all instances, the principle of the generation of electricity. To illustrate further this principle, let's analyze the action within a cell, a simple source of electric energy. A piece of zinc is suspended in a suitable container. Its atoms are neutral until a chemical solution is added. Then some of the zinc atoms go into the solution, leaving a few of their electrons behind in the metal. The zinc becomes strongly negatively charged. Now a piece of electrically neutral copper is put in a chemical solution in another container. The copper will become very weakly negative. Since the copper has a smaller negative charge, it is positive with respect to the zinc. And if the two metals are connected, the electrons will surge from the zinc to the copper, and the charges will become equalized. This momentary current has little practical value. However, if we now connect the solutions, the charges in the solutions will become equalized, and the metals or terminals will be charged. We will then have an unbalanced condition of the electrons in the metals capable of producing a continuous flow of useful electric current. All of the work performed by electricity requires a flow of current. So let's see what principles are involved when current flows. There are three related to the flow of electricity. They are pressure or voltage, current intensity, and resistance. First, let us consider pressure. With nature always trying to maintain an electrical balance, there is a tendency for any negatively charged object to throw off or repel its excess of electrons, and for a positively charged object to attract electrons. This urge to maintain an electrical balance is potential electric energy. And since this potential energy is a repelling and attracting urge caused by opposite charges, its force or pressure is equal to the difference in the charges. It is called the difference in potential or potential difference. The unit of pressure or potential difference is the volt. The voltage, then, is always the potential difference at the negative and positive terminals of the source of the electric energy. It represents the difference between the number of extra electrons at the two terminals. And when a suitable path is provided, the potential difference causes the electrons or current to flow from one terminal through the conductor to the other terminal. To explain how this works, let's review the action of the atoms and their electrons in a piece of metal, where we saw swarms of electrons moving freely in all directions about the atoms. Substances in which this takes place are good conductors of electricity. If an outside electric pressure or voltage is applied to a conductor, the electrons will move predominantly in one direction. The effect is that electrons move from the negative to the positive terminal. This is the electric current. The unit of electric current is the ampere. 1 amp, now hold on to your hat, 6,300,000,000,000,000,000 electrons passing any given point in 1 second. Current, or amperage, then, is the number of electrons that pass a given point in a given time. And now the third factor, resistance. This factor is controlled by the nature of the material through which the electrons flow. Again, going back to the motion of electrons in a metal, we said that they moved freely about and among the atoms. However, even in the best of conductors, some of the electrons collide with the atoms, tending to retard the movement of the electrons. This is the cause of electric resistance. Collisions are more probable in some metals than in others. Therefore, different metals offer different degrees of resistance to the flow of electrons. For example, copper has low resistance. It permits the electrons to flow freely with few collisions and is therefore a good conductor. Iron offers more resistance than copper. Collisions with the atoms are more frequent. In some substances, no electrons are free to move around as in the metal. All of the electrons stay with their atoms so that no current can flow. These substances are the insulators: glass, porcelain, rubber, and many others. The collisions that the electrons have with the atoms set the atoms into more violent vibration. This makes the metal hotter. If there are enough of these collisions, the metal will radiate heat and light. Heat and light from electrical sources, then, can be obtained as the result of resistance in some metals. The unit of resistance is the ohm. Its value is best understood when its relation to the other factors is explained. A pressure of 1 volt produces a current of 1 ampere through a resistance of 1 ohm. Whatever the source or the magnitude of electric energy, these factors always have the same relation to each other. So, in order to supply our great demands for electric power, we must have facilities for generating great currents at sufficient pressures to overcome the resistance of the lines, as well as to do the work. Power for industry, transportation, and light, as well as for many other conveniences we use in our daily lives. Our own sources of current able to perform these amounts of work are the electromagnetic generators. In order to explain the manner in which electricity is produced by electromagnetic generators and used in most electrical machinery, let's have a look at magnets and magnetic fields. The Earth itself is a magnet. So are the tiny electrons. All of the electrons in any object are tiny magnets. When a predominant number of these tiny magnets point in one direction, we have an extremely small magnetized block called a magnetic domain. Magnetic material, that is, material capable of being magnetized, is made up of such domains, pointing in all directions. When these domains all point in the same direction, we have a magnet. In some materials, such as copper, the tiny magnets of the electrons never line up. These materials are non-magnetic, cannot be magnetized. Every magnet has a magnetic field. Magnets may be made in various shapes to provide convenient and strong fields. To understand how a magnetic field is useful in the generation or application of electricity, Let's go back to the electron, Mr. Electron, and watch him move across the magnetic field. Will you do it again, Bud? Now notice, as he enters the magnetic field, he's deflected from his original course. His deflection depends upon his velocity. Now, as we have previously shown, conductors have many free electrons. And if a conductor is moved across a magnetic field, the mechanical action causes the electrons in the wire to be deflected, just as we saw Mr. Electron deflected. This, in effect, establishes a negative and a positive charge at the ends of the conductor. We now have two charged terminals capable of producing a continuous flow of electric current, just as we had in the cell. This is accomplished in practice by providing a means of continuing the movement of a conductor within a magnetic field. In all electromagnetic generators, regardless of size, the same principle is used to generate electricity. The deflection of electrons in a conductor moving across a magnetic field. The same magnetic fields and forces are also used in making an electric current perform useful mechanical work. Remember that an electron moving across a magnetic field is deflected. If the electron were moving in a wire, as when electric current flows, the deflection of the electron would cause it to push against the wire, tending to move the wire. Billions upon billions of these tiny pushes combine to provide the force. The stronger the current, or the greater number of electrons, the greater the force moving the wire. These forces on current-carrying wires in magnetic fields furnish the power for all electric motors, from the simplest to the most complex, from the smallest to the largest electric motors. The principle is the same. The deflection of electrons flowing in current-carrying wires by magnetic fields. In fact, interaction between the magnetic fields and the electrons is the basis of all electric devices. And now we may summarize that the billions and billions of atoms of which the universe is built are composed of positive and negative electric charges. That these charges are normally balanced in matter. That by unbalancing these charges, electric energy is made available. That the urge of nature to restore this balance creates electric pressure. And that the response to this urge, the action of the restoration of the balance, is a flow of electric current. The flow of electric current, then, is simply movement of electrons away from objects that have acquired a negative charge to objects whose charge is relatively positive. It's this principle that has made possible the countless electric devices which contribute to the comfort and fulfillment of richer and happier living today. Devices which will expand that to unlimited horizons in the future. Devices whose operation is dependent upon nature's design for matter, demanding that matter itself shall always seek a state of new electrical balance.
Modern data processing systems like these use thousands of magnetic cores. These cores are small, rugged, and they consume less power than most of the other devices that are used in these systems. You'll also find magnetic cores in automatic equipment employed for communication, fire control, cryptography, and high-speed computation. What are magnetic cores?
They are tiny rings of nickel alloy or other magnetic materials.
They have replaced vacuum tubes for many important functions in data processing systems. Cores come in a variety of sizes and in two basic types.
The ferrite type of core is molded from compounds that magnetize easily and is used to provide data processing systems with their memories. The metallic ribbon type consists of a non-magnetic spool wound with a thin ribbon of highly magnetic alloy. This type is used in operating circuits of ADP systems. Both types of magnetic cores are remarkably adaptable to the language of data processing. Many ADP systems use the binary system of numbering, which employs just two digits, 0 and 1. These two digits are called binary digits, or bits for short. A bit is either a 0 or a 1, nothing else.
Why do we use binary? Because a bit can be represented by any bistable device, and a magnetic core is a bistable device.
Bistable, because it can be magnetized in two directions. When the magnetic lines of force point in one direction around the core, they are a positive magnetic flux, and the core is said to hold a binary 1. If the direction of magnetism is reversed, the flux becomes negative, and the core holds a binary 0. However, remember that this arbitrary definition of positive magnetic flux representing binary 1 and negative magnetic flux representing binary 0 may be reversed in some systems.
So far, we've been establishing the function of magnetic cores. They store binary digits, or bits, 0 or 1. Now we're going to see how they do it, and also how they transfer bits from one core to another.
To explain how cores store binary digits, we must know how they are constructed. Around the core is wrapped a conductor. Current flowing through the winding produces a magnetic field around the conductor. Because the core is made of highly permeable material, it forms a path for the magnetic lines of force. Because it is ring-shaped, the path it forms is a closed loop. The conductor here is wound so that current flowing in this direction produces a positive flux, setting the core in the binary 1 state. Current flowing in the opposite direction produces a negative flux, which sets the core in the binary 0 state. To show the polarity of the winding in a core diagram, we mark one side with a black dot. By definition, current that flows into the winding from the dot side sets the core to 0. Current flowing into the non-dot side sets the core to binary 1. Remember, non-dot current for 1 and dot current for 0. Any winding around the core obeys the laws of electromagnetism. The magnetizing force it exerts is proportional to the amount of current flowing through it measured in amperes times the number of turns in the coil. Or, as it is usually expressed, the ampere turns. Since the number of turns in this winding is constant, we can simplify the rule here. The magnetizing force exerted by the winding on the core is proportional to the winding's current. Suppose we increase the amount of current. Will the total magnetism of the core also increase?
It will, but not proportionately, as we'll see on this graph. We're going to take a minute and trace the magnetization curve of a core, because in this way we can point up some of the characteristics that make cores so useful.
We measure the magnetism of the core in terms of its flux density, which is the number of magnetic lines of force per square inch. The horizontal axis will represent the magnetizing force of the winding. Remember that the magnetizing force is the cause and the flux density is the effect. Initially, a relatively small amount of magnetizing force produces a relatively high flux density. The curve on the graph will begin like this. But as we increase the magnetizing force, the curve flattens out because we are adding proportionately less to the flux density. Further increases in magnetizing force will have no appreciable effect on flux density. The symbol for magnetizing force is the letter H. The symbol for flux density is the letter B. The relationship between magnetizing force and flux density for any given core material is represented by its BH curve. This is the point of saturation. The core is holding just about all the magnetism it can hold. We've been applying a positive magnetizing force here, which produced a positive flux density and brought the core to a state of positive saturation. If we now reduce or stop the magnetizing force, for all practical purposes, there is no change. The core material retains most of its magnetism. Here's how we plot this fact on the graph. The BH curve is brought back to the zero line on the horizontal scale. Watch the difference in flux density on the vertical scale near the plus B. It's negligible. This, then, is the amount of remaining magnetism. This amount is known as the residual magnetism of the core material. The magnetism that remains after the force that brought it about is removed. When non-dot current sets the core to the binary 1 state, the residual property keeps it that way, indefinitely. Suppose there is a second pulse of non-dot current. It will have no practical effect on the core because the core is already saturated with positive magnetism. But if we send current through the other way, into the dot side of the winding, then, of course, the core's state will change. To plot the effect, we'll extend our graph. With dot current, we're applying a negative magnetizing force represented by minus H. Negative flux density is symbolized by minus B. We need a certain amount of negative magnetizing force to overcome the existing positive residual magnetism in the core. The amount needed is called the coercive force. At this point, the material contains no magnetism. The flux density is 0. Adding more negative magnetizing force produces a negative flux density. And again, the core is brought to a state of saturation, negative saturation. If we reduce or stop the magnetizing force now, there will be little effect on the flux density of the core. The BH curve returns to 0 on the horizontal magnetizing force scale, but it remains at almost the saturation level on the vertical flux density scale. In other words, there is residual magnetism in the negative direction too. Therefore, when dot current is fed into the core, magnetism builds up and the core is set to binary 0. Residual property keeps it there. To switch the core, we apply a positive magnetizing force. Enough first to cancel out the negative residual magnetism. That is, to act as a coercive force in the opposite direction. And then, by adding more positive magnetizing force, we can bring the core material back to a state of positive saturation. We have now plotted the positive and negative magnetization of a core. The original S-shaped curve is produced only when we are first magnetizing the core from a completely unmagnetized state. From then on, we're concerned only with the rectangular loop, which tells us the limits of saturation that can be reached with dot and non-dot current. Also, the amount of magnetism that will remain in the core after the current stops. The word hysteresis comes from a Greek verb meaning to lag behind. A hysteresis loop, therefore, shows how much magnetism remains behind after the force that produced it is gone. The shape of the loop indicates the ability of a particular core material to retain magnetism. Shallow rounded loop, low residual magnetism. A core of this type obviously requires less force during a switch from one state to the other. Rectangular loop, high residual magnetism, a greater amount of force needed. If a core with a rectangular hysteresis loop is in the binary 0 state, we're going to have to apply a substantial pulse of non-dot current in order to set it to binary 1. A lesser pulse just won't make the switch. Now, how do we get information out of a core? By means of a second winding. Let's follow the transfer of information from input to output. Assume the core is in a state of positive residual magnetism, in the binary 1 state. To change the core to binary 0, we send current into the dot side of the input winding. Dot current switches the core to binary 0, reversing the direction of the magnetic lines of force. If we diagrammed it, we'd see the positive residual field collapse entirely and a negative field build up to saturation. Anytime a magnetic field builds up or collapses across a conductor like this winding, the movement of the lines of force induces a voltage in the winding, and current flows. Observe the direction of current flow, out the top of the winding. The way these two conductors are wound, a pulse of current sent into the bottom of the input winding results in a pulse of current going out of the top of the output winding. We used a dot to keep track of the polarity of the input winding, and a similar dot will establish the polarity of the output winding. This gives us another rule about the dots in a magnetic core diagram. When dot current moves into the input winding, it causes the current to move out the dot side of the output winding, provided the input current produces a change in flux. For example, our core is now set at binary 0, so a second pulse of dot current will have no practical effect. The core is already at the level of negative residual magnetism. There is no change in flux, and therefore no output current. However, if we send current in the opposite way, into the non-dot side of the input winding, the direction of flux in the core is reversed, switching it to binary 1, and produces a current that flows out of the non-dot side of the output winding. To repeat, a non-dot current input results in a non-dot current output. Remember these two rules. Dot current in results in binary 0 and dot current out. Non-dot current in results in binary 1 and non-dot current out. Now suppose we want to send non-dot current into the core, setting it to the binary 1 state, but we don't want to send current out, at least not yet. By connecting in a second core on the right, we can see more clearly what the problem is. Now, the first core's output winding is directly connected to the input of the second core. This input has been wound so its polarity is the same as that of the input of the first core. The dot side is below. In a typical core circuit, current flows in only one direction, into the input of the first core. We'll take the non-dot side for our example. We'll assume that initially, the left core is set to 0 and the right core to 1. All we want to do is store a binary 1 in the left core. Watch what happens with the circuit as we have it. Current flows into the non-dot side of the first core's input. The first core is switched to 1, as we wanted. But this produces current to flow out of the non-dot side of the first core's output, along the circuit and into the dot side of the input winding on the second core, switching that core to 0, which we did not want. If we are going to control the transfer of information from one core to another, we need something in the circuit that will block the flow of the current, and do it selectively. The device commonly used is a crystal diode, which has a high resistance to current flow in one direction, the back resistance, and practically no resistance at all in the forward direction. Any unidirectional device or arrangement will serve the purpose, and we'll symbolize this with a general symbol for one-direction flow. The arrow points in the direction in which it allows the current to flow. Current coming the other way meets the back resistance of this device and is blocked. With such a device in position in the circuit, the second core is effectively isolated from the first. We'll create the same conditions we had before. The first core is initially set to binary 0, and the second to binary 1. We send non-dot current into the input winding of the first core, switching it to 1. But, due to the back resistance of the electronic device, no current can flow against the arrowhead. No current, no flux change, no change in the second core from binary 1 to binary 0. Thus, we have changed the binary state of the first core and retained the binary state of the second core by the use of this unidirectional device. How can we switch either core to 0? We've said that current flows into the input of the first core on the non-dot side only, and this would be typical in a core circuit. The device will allow current to flow through it in its forward direction only, as we've set it up here. That means that current can flow into the non-dot side of the second core's input, but not into the dot side. What we need for dot current is a shift winding on each core, wound so the dot side is at the left in our diagram. The shift winding shifts or transfers bits from one core to the next, as these two will demonstrate. But we'll complete our diagram first by giving the second core an output winding that is identical with the first core's output. And for this example, we'll assume that both cores are in the 0 state. All right, we'll follow the events in their proper sequence. A non-dot input sets the first core to 1. Nothing happens to the second core. Current flow in this direction sets a core to 0, but that's where this core is already. We can hold the binary 1 in the first core as long as we wish. When we're ready to transfer it out, we send a pulse of current into the dot side of the shift winding, and 3 things happen. The first core switches to 0. Current flows out of the dot side of the first core's output, through the one-way device, and into the non-dot side of the second core's input. And the second core switches to 1. We have now transferred a binary 1 from the first core to the second, and controlled the time of the transfer to the exact moment we want it. The binary 1 may be stored here, or again, a shift pulse may be applied to make the transfer to the next core along the line, thus clearing this core back to binary 0. However, there is one final problem to consider here. A shift pulse will induce a voltage not only in the output winding, but also in the input winding. Current will flow out of the dot side of the input back toward the first core. The one-way device won't stop it because it's going around the circuit in the direction it allows. This backward flow of information would, if unchecked, switch the first core, interfering with its operation. It is checked, however, by the design of the output winding. The output winding of the first core has many turns, in contrast to the input winding of the second core, which has relatively few turns. The ratio may be as high as 12 to 1. Consequently, the small current produced in the second core's input meets a high impedance when it flows back to the first core's output. There just isn't enough current to provide the force necessary to switch the first core. We have been diagramming the single diode transfer loop, the simplest and most basic of the circuits that transfer bits from one core to other cores. The diagram we have been building up is a schematic, but there's an easier way to represent these loops.
Logical diagrams eliminate the complex details found in schematics by concentrating on what the magnetic core circuit does. Its logic, or reason for being there. Only a few symbols are needed for logical diagrams, and they're easily understood.
A circle represents a core. An arrow pointing into the circle is an input. An arrow pointing away, an output. A binary digit inside the core indicates its state, 0 or 1. If the bit is placed in front of an input arrow, it shows the state to which that input will set the core, in this case, 1. A bit placed behind an output arrow means that when the core is switched to this state, an output will be induced. Here the core must be switched to 1 for an output to occur. If we remember that initially the core is either at 0 or 1, we'll see that these arrows and bits tell us 4 things about this circuit. If the core is initially 0, the input switches it to 1, and an output occurs. If the core is initially 1, there will be no switch. Therefore, no output. since there will be no change in the flux of the core.
Other symbols used for logical diagrams are just as simple. For example, if we wish to show an input that will set the core to 0 using direct current, the arrowhead is closed. In our discussion, we've been dealing with pulse current, shown by open head arrows. Double arrowheads mean an override input, an input that will hold the core to the indicated state, despite the simultaneous presence of other inputs. The letter T is used to designate time. This override pulse will hold the core to 1 at a moment in time identified as T1. Other letters serve to label individual inputs and outputs where several may be present. We can relate an input to an output with the capital and small form of the same letter. Thus here, where the core is initially 0, and input Q comes in at time T1 and switches it to 1, an output occurs. This output is identified by small q. Now let's take another look at the logical diagram of the single diode transfer loop. It gives us the whole story very quickly. An input pulse sets the first core to binary 1, unless it's there already. The core stays at 1 until a shift pulse comes in at time T1 and switches the core to 0. This switch induces an output pulse in the first core's output winding, which causes the second core's input winding to set that core to 1. In effect, a binary 1 has been transferred from the first core to the second, where it's stored until at time T2, another shift pulse clears the second core back to 0. We can draw logical diagrams like this of any magnetic core circuit, and we depend on them for a clear understanding of the work done by the circuit. In this picture, we've been dealing with the basic properties of magnetic cores, memory units, and a variety of operating circuits. Later, you'll be seeing how they work. They've demonstrated their efficiency and reliability in dozens of applications. They conserve space and power. They operate with precision at high speed. In fact, the development of the modern computer has been due in large part to the techniques devised for using these remarkable cores.
What's one thing that all of these devices have in common? Well, they all filter something. We filter the air we breathe with air conditioner filters, the water we drink with water filtration systems. We filter the air, the oil, and the gas that our cars use, and then we try to filter out the pollutants that result when we use the car. We filter light with sunglasses and shades, and we even put filters on some things that we shouldn't even be using in the first place. As a matter of fact, you name it, and I'll bet you that somebody's thought of a way to filter it. We use a lot of filters in electronics too, and all of them basically serve the same purpose as the other filters we've been talking about. They pass what we want to pass and reject everything else. Electronic filters keep noise and interference out of your radio and TV sets. They allow you to listen to high-fidelity recordings in FM stereo. They make certain that a radar set electronically sees only what it's supposed to see. As a matter of fact, it's probably safe to say that there's not a single piece of electronic equipment that doesn't use a filter of some type. Basically, filters are designed to do one of four jobs. One, to pass all frequencies below a specified value and reject all those above that value. Two, to pass all frequencies above a specified value and reject all those below that value. Three, to pass a selected band of frequencies while rejecting all others. And four, to reject a selected band of frequencies while passing all others. All electronic filters fall into one of those four categories, except for a few very specialized cases. And it's made possible by these simple components: capacitors and inductors. In this lesson, we'll discuss how these components can be connected together in series to provide filtering action. In a later lesson, we'll discuss parallel filters. Before we begin, let's look at the terms we'll be using in discussing filters and define those that are new to you. This response curve shows all of them: band pass, bandwidth, cutoff frequencies, and the attenuation bands. The band pass, you'll recall, are those frequencies that fall within this area on the response curve, between the half power points. In this case, the band pass is from 5 to 7 kilohertz. The bandwidth then, or the width of this band of frequencies, is 2,000 hertz, or 2 kilohertz. The cutoff frequencies are those frequencies below or above which there is no usable output from the filter. Here, below the cutoff frequency of 5 kilohertz, there's no usable output, and above the cutoff frequency of 7 kilohertz, there's no usable output. The attenuation band is used to describe all those frequencies that do not pass through the filter, all those frequencies above and below the high and the low frequency cutoff points. A basic filter circuit is the inverted L configuration, so called because it looks like an upside down or an inverted L. By plugging into the series and the shunt positions of this circuit the correct values of inductance and capacitance, and in some cases resistance, we can accomplish all four basic filtering actions. Now, in this circuit, total current will always pass through the series component. However, only part of total current passes through the shunt component, the rest going through the load impedance. The important point to note in this arrangement, though, is that the voltage felt in the output voltage, is the same as the voltage across the shunt, because they're in parallel. And the voltage across the shunt is dependent on the voltage developed by the series component, because the voltage across the shunt is equal to the total applied voltage minus the voltage drop across the series component. Thus, this circuit acts like a simple voltage divider. Now, we can easily demonstrate this basic principle of filters on our trainer. The equipment that we'll be using for our demonstration is an oscilloscope, little circuit board or trainer, and a signal generator. Now, the signal generator will deliver a 10-volt signal to the trainer. We can control the frequency out of the signal generator with this knob. But the output voltage is fixed at 10 volts and will be supplied to the trainer from this test point up to this connector. Now, from this point, the 10-volt signal is supplied to two places, the upper connection here and a lower connection here. Now, the upper connection goes directly over to this point, and as you can see is tied directly in to the A trace or the top trace of the oscilloscope. Now, this shows or displays the output from the signal generator at all times, the top trace of the scope, and is connected with this connector to this point. Now the middle connector here is used to provide a synchronization voltage for our oscilloscope, which, as you can see, we need. I'll just plug that back in. That's the top trace. Remember, it always displays the output directly from our signal generator. Now the lower connection here, this is where we'll connect our filter components. The series component here, the shunt component here. We'll take our output across the shunt component, and it will be displayed on the B trace, or the lower trace, of our oscilloscope. Now, as you can see, we have no output at this time because, of course, we have no components plugged into our filter circuit. Notice also that the oscilloscope, a little trainer, and the signal generator are all grounded together. To show how a simple voltage divider can provide filtering, we'll use two variable resistors, just like this one. Now you'll note that this is nothing more than a variable resistor that I've connected with a couple of test leads so that I can plug it directly into my trainer for use during the demonstration. Now we'll put one here in the series position and one here in the shunt position to illustrate how the voltage dividing principle will work to affect the output voltage. Well, here, I'll just plug this one in, the shunt position, like that, and there. And we'll put this one in the series position, like this. Now that audio tone that you're hearing in the background, that audio tone results because I have a loudspeaker connected to this point on the trainer. Now this is the output of our trainer, so that the tone will always indicate whatever is coming through the circuit. You'll also be able to see the output displayed on our scope, so you'll have two checks to determine the effect of our filter components on our output voltage. I think in this way you'll be able to understand the operation a little better. Now remember, the generator output, which is applied here, will go through the series component, then down through the shunt component to ground, and we'll be taking our output across the shunt component. Now first, let's set our series resistor to 0 resistance or opposition, and we'll set our shunt resistor to maximum opposition, just like that. Thus we have a short circuit here in the series position and maximum resistance here in the shunt position. Now this should give us maximum output voltage, and as you can see, it does. You can also hear the fact that we're getting our audio tone clearly through this circuit now. We have 10 volts in our input, 10 volts directly from the signal generator, and we also now have 10 volts in our output. So we can conclude that to have maximum output voltage requires minimum series opposition and maximum shunt opposition. Now let's set our series resistor to its maximum position and the shunt to its minimum position. Now, as you can see, we have no output at all, and you can also notice by the fact that we have no audio tone that there is 0 output. We have all our voltage now being dropped across the series component. Our conclusion is then that to have minimum output voltage requires maximum series opposition and minimum shunt opposition. This is what we want our filter to accomplish. For those frequencies we want to pass through the filter and on to the output, say 500 hertz, we'll want the shunt opposition to be maximum, like this, and the series opposition to be minimum, like this. Thus, this frequency, 500 hertz, will pass through the filter and on to the output. Now, for those frequencies we want to reject and not allow to pass through the filter, say 700 hertz, we'll want the series opposition to be maximum, like that, and the shunt opposition to be minimum. Thus, this frequency, 700 hertz, is now being rejected. The voltage dividing principle works. We can pass or reject specific frequencies, but since resistors are not frequency-sensitive devices, this system is not very practical, is it? The circuit is now rejecting 700 hertz, all right, but it's also rejecting all other frequencies as well. If we set it to pass one frequency, say 500 hertz, by selecting maximum shunt opposition and minimum series opposition, like this, well, it not only passes the frequency we want to pass, it passes every other frequency as well. What we need in our filter circuit, then, are components that will react automatically to input frequency changes by adjusting their own oppositions and thus altering the output voltage. In other words, we need frequency-sensitive components. Inductors and capacitors fit this need. They are frequency-sensitive. X sub L, inductive reactance, is the opposition an inductor offers to current. At a low frequency, the inductive reactance is small. At a high frequency, it's large. X sub C, or capacitive reactance, is the opposition a capacitor offers to current. At a low frequency, it's high. At a high frequency, it's low. By plugging these two components into our circuit, we can meet the requirement for frequency-sensitive components to operate the filter. Action we will demonstrate X sub C, or capacitor. X sub L, inductive reactance, is the opposition an inductor offers to current. At a low frequency, the inductive reactance is small. At a high frequency, it's large. X sub C, or capacitive reactance, is the opposition a capacitor offers to current. At a low frequency, it's high. At a high frequency, it's low. By plugging these two components into our circuit, we can meet the requirement for frequency-sensitive components to operate the filter. The first filter action we will demonstrate is the passing of low frequencies and the rejecting of high frequencies. In other words, we'll have a low-pass filter. Now, from what we've previously established, in order for our circuit to pass low frequencies, the series opposition must be low at the low frequencies. The inductor, then, must be our choice for the series component, because at low frequencies, its opposition is low. Then, too, the series component should be able to reject the high frequencies. The inductor can also do this because its opposition is high at the higher frequencies. So the series inductor is always used to pass low frequencies and to reject high frequencies. The shunt opposition, however, must work the other way. That is, it must be large at low frequencies so it can develop our output voltage, and it must be small at high frequencies to shunt them away from the output. The capacitor fills the bill for our shunt component. At low frequencies, it offers a large opposition. At high frequencies, a small opposition. So the shunt capacitor is always used to pass low frequencies and reject high frequencies. This circuit, then, a series inductor and a shunt capacitor, serves as an inverted L low-pass filter. It passes low frequencies rejects high frequencies. All right, now let's hook up the trainer in the configuration we've just illustrated, that of the low-pass filter. First, we need a capacitor in the shunt position. Okay. Then, the inductor goes in the series position. And there's our output from the filter. At this frequency, we do have an output. Now let's check the overall frequency response of this filter circuit, the low-pass filter. Now you'll notice down at the low frequencies, well, I'm down around 200 hertz now, you'll notice that I do have an output. I have 10 volts on the input directly from the signal generator, and on the B trace, the lower trace, I show 10 volts of output from my filter circuit. So we're passing the low frequencies because this is a low-pass filter. As I increase the frequency, though, you'll note that at about 600 hertz, the output starts dropping off. Now we're beginning to reject higher frequencies, which again the low-pass filter must do, must reject the higher frequencies. Here at about 1200 hertz, you can see that, well, I hardly have anything at all in the output, so we're rejecting these higher frequencies. With a 10 Henry inductor and a 0.01 microfarad capacitor as my filter components, I'm passing all frequencies from, well, about 1 hertz on up to about 600 hertz, on up to about this point. But those frequencies above 600 hertz are not getting through. They're being rejected by our filter circuit. Plotted on a graph, the output voltage looks like this. Here, at about 600 hertz, the output drops below 7 volts. Now remember, I had an input of 10 volts. So anything in the output less than 0.707 of this 10 volt value, or in other words about 7 volts, is not considered usable output from this filter. However, this is not true in all cases. Actually, the output voltage from the filter is still considered usable if it operates the load device. But in most cases, the output voltage should be at least the effective value of the input voltage. So this then is the cutoff frequency for this particular filter, 600 hertz. Frequencies below this value are said to be in the bandpass of this circuit. Those frequencies above this value are in the attenuation band. Of course, the cutoff frequency can be changed simply by changing the value of the filter components. Our next filter requirement is to pass high frequencies and reject low frequencies. In other words, to reverse the action of the low-pass filter we've just illustrated. Now, it's only logical to assume that the action of the filter can be reversed simply by reversing the series and shunt components. In other words, we'll put the inductor now in the shunt position and the capacitor in the series position. All right, let's do that then. Let's reverse the position of the series and shunt components on our trainer and then see what the frequency response will be. All right, we'll just unplug the inductor and the capacitor. Now we'll place the inductor in the shunt position now, just like that, and the capacitor we'll place in the series position. All right, capacitor in the series position, inductor in the shunt position. What should we expect our output response to be? Well, we know that in order to reject low frequencies, the series opposition must be large at low frequencies. Well, this is true of the capacitor. It offers very large opposition to low frequency currents. But at high frequencies, the ones we want to pass, the series opposition must be small. Again, this is what the capacitor provides. So, a series capacitor is always used to pass high frequencies and reject low frequencies. Now, the shunt opposition must be minimum at low frequencies to shunt the output voltage, and maximum at high frequencies to develop the output voltage. And this is what the shunt inductor does. So the shunt inductor is always used to pass high frequencies and reject low frequencies. This circuit then is an inverted L high-pass filter. It passes high frequencies, rejects low frequencies. Okay, let's check this out now with our demonstration. Now, as I vary the input frequency from a low of about, let's say 200 hertz, you can see that nothing much below, well, about 600 hertz, which is at this point, is getting through our filter. Frequencies above 600 hertz are passing through, though. We're passing the high frequencies. Now, since we've not changed the value of the components, our cutoff frequency is still the same, 600 hertz. That's our high-pass filter. We're passing high frequencies, rejecting low frequencies. All the frequencies below our cutoff frequency of 600 hertz are being rejected by this filter. Those above are being passed. But suppose we want to reject both lows and high frequencies and only pass a small band of frequencies right around 600 hertz. You'll recall that this was the third filter configuration that we mentioned earlier. Using this inductor and this capacitor, and with the addition of this resistor to the circuit, let's design a filter circuit that will pass a band of frequencies between, say about 500 hertz and 700 hertz, with a center frequency of 600 hertz. Now, we're only going to be passing this small band of frequencies. The rest of the frequencies we want to reject. Now, what does this mean in terms of our series and shunt oppositions? Well, we know that in order to pass 600 hertz, our series opposition must be low at a frequency of 600 hertz. But at frequencies above and below that, the series opposition must be very high in order to reject those other frequencies. Well, at 600 hertz, the inductor we've been using in our demonstration has an opposition of 31,400 ohms. The capacitive reactance of the capacitor we used at 600 hertz is also 31,400 ohms. Now, individually, neither component, neither the inductor nor the capacitor, can do the job of passing a band of frequencies around 600 hertz. But when we place them together in series, like this, a rather remarkable thing occurs. Since inductive reactance and capacitive reactance are opposite forces, they're 180 degrees out of phase, and since in this case they're equal values, 31,400 ohms at 600 hertz, the combined reactances exactly cancel each other. So the net effect of the combination is to offer minimum opposition to 600 hertz. In other words, it's simply a series tank circuit, and as you've learned previously, a series tank circuit offers minimum opposition to the resonant frequency and maximum opposition to all other frequencies. Now, the shunt impedance in this case can be purely resistive, simply a resistor, since its only use is to develop the output voltage. Now, since the series tank opposition is minimum at the resonant frequency, circuit current will be maximum. This current will flow through the shunt resistor and develop the output voltage. At all other frequencies, however, the series tank opposition will limit circuit current to the extent that very little current will flow through the resistor, thus very little output voltage will be developed. Okay, the generator is connected to the inductor, these leads here, here's our inductor, and then to our capacitor, down through this resistor and this little shorting wire, and to ground. Now, at frequencies below 500 hertz, the output drops to minimum, as you can see. Now, as I increase the generator frequency, you'll note the output start to rise until at about 600 hertz, the output is maximum. As a matter of fact, it's about the same as our input frequency at this point. Now, further increase in frequency causes the output voltage to decrease again. So we're passing just this small band of frequencies between 5 and 700 hertz. Now, on a graph, you can see that at about 500 hertz, the output voltage is 7 volts. And again, at about 700 hertz, the output drops back to 7 volts. So in between these two frequencies, we have usable output from the filter between 5 and 700 hertz. So 500 hertz and 700 hertz are the cutoff frequencies, and the band pass of this filter is 500 to 700 hertz. The bandwidth is 200 hertz. These frequencies are in the band pass of this filter. All those above and below the cutoff frequencies are in the attenuation band. Now, earlier we found that we could make a low-pass filter perform as a high-pass filter simply by reversing the position of the series and shunt components. Well, the same thing is true of this band-pass filter. By reversing the components, as we've done, we can cause the circuit to now reject a band of frequencies and pass all others. In other words, it becomes a band reject filter. Let's see how. Okay, we simply put the resistor in the series position. We're reversing its position, and the LC tank goes in the shunt position, just like that. Now, the series component, the resistor, has no effect on the input frequency because it's not a frequency-sensitive component. However, the shunt component, the LC tank, is frequency-sensitive. Remember, at the resonant frequency, the tank circuit's opposition is minimum. Now, if we have minimum opposition, then we'll have maximum current flow, and this same current must flow through the series component. Thus, the series component, the resistor, will develop a maximum voltage drop. Now, with maximum voltage dropped here, then we must have minimum voltage dropped across the tank. This means, of course, that the output voltage is also minimum because they're in parallel. We're still dividing the voltage. Now remember, at resonance, maximum voltage is developed by the series component, the resistor. At frequencies above and below resonance, however, the tank opposition now becomes maximum. Now, if the tank opposition is maximum, it then will develop the maximum voltage drop across it. So at frequencies off resonance, the output voltage will be maximum. Thus, this filter configuration will reject frequencies right around resonance, but pass all others. Let's demonstrate this. The output of the generator is connected to the resistor and through this little shorting wire. This is our series component. Then our shunt component, the inductor and the capacitor, and then on down to ground. The output is taken across the shunt component, which in this case is the tank circuit. All right, at frequencies below about 500 hertz, the output from the filter is maximum. However, when we approach 600 hertz, the output drops off to practically nothing. Above 600 hertz, though, the output rises to maximum again. This filter, then, the band reject filter, is now rejecting a band of frequencies around 600 hertz, but passing all others. The graph of output voltage shows that this filter rejects frequencies from 500 to 700 hertz, but it passes all others, those below 500 hertz and those above 700 hertz. The cutoff frequencies are here, 500 and 700 hertz. Those frequencies from 0 to 500 hertz and from 700 hertz on up are in the band pass, and those frequencies between 500 and 700 hertz are in the attenuation band. All right, that's our basic filters. Remember, a low-pass filter is designed to pass low frequencies, reject high frequencies. The L-section filter uses a series inductor and a shunt capacitor. A high-pass filter is made by simply reversing the position of the series and shunt components. Now the high frequencies are passed and the low frequencies are rejected. A band-pass filter used a series tank circuit and a shunt resistor to pass a selected band of frequencies and reject all others. A band reject filter rejected a band of frequencies while passing all others. This was accomplished by reversing the position of the series and shunt components of the band-pass filter. The resistor became the series component and the tank the shunt component. Now in this lesson we've discussed how series LC filters are nothing more than simple arrangements of the components in the series and shunt configurations. In our next lesson we'll discuss how parallel LC tanks can be used to accomplish the same filtering actions. Tank opposition is maximum, it then will develop the maximum voltage drop across it. So at frequencies off resonance, the output voltage will be maximum. Thus, this filter configuration will reject frequencies right around resonance, but pass all others. Let's demonstrate this. The output of the generator is connected to the resistor and through this little shorting wire. This is our series component. Then our shunt component, the inductor and the capacitor, and then on down to ground. The output is taken across the shunt component, which in this case is the tank circuit. All right, at frequencies below about 500 hertz, the output from the filter is maximum. However, when we approach 600 hertz, the output drops off to practically nothing. Above 600 hertz, though, the output rises to maximum again. This filter, then, the band reject filter, is now rejecting a band of frequencies around 600 hertz, but passing all others. The graph of output voltage shows that this filter rejects frequencies from 500 to 700 hertz, but it passes all others, those below 500 hertz and those above 700 hertz. The cutoff frequencies are here, 500 and 700 hertz. Those frequencies from 0 to 500 hertz and from 700 hertz on up are in the band pass, and those frequencies between 500 and 700 hertz are in the attenuation band. All right, that's our basic filters. Remember, in our first lesson on simple filters, we found that almost all filters can be classified as low pass, to pass a range of frequencies up to a certain value and reject those above that value; high pass, to pass a range of frequencies above a certain value and reject those below that value; band pass, to pass a selected band of frequencies while rejecting all others; and band reject, to reject a selected band of frequencies while passing all others. We also found that almost all filters are simple combinations of inductors, capacitors, and resistors. It was the reaction of a particular combination of these components to frequency that produced filtering action. For example, this low-pass L-section filter has an inductor in the series position, a capacitor in the shunt position. The inductor offers a small impedance to low frequencies, a large impedance to high frequencies, thus will pass lows, reject highs. The capacitor works just the opposite. It offers a large impedance to low frequencies and thus develops a large voltage across it. Since that output is taken across the capacitor, the output voltage is large at low frequencies. At high frequencies, its impedance is small and it does not develop a suitable output voltage. No output at high frequencies. We found that we could reverse the action of the filter by reversing the filter components. The capacitor in the series position offers a large impedance to low frequencies and blocks them, and a small impedance to high frequencies and passes them. The inductor in the shunt position offers a small impedance to low frequencies and does not develop a suitable output voltage, while at high frequencies its impedance is large and thus it will develop an output. A series tank circuit placed in the series position of the filter will pass a band of frequencies around resonance and reject those above and below resonance, because a series tank offers minimum impedance to frequencies close to resonance and will pass them, but to all other frequencies it offers maximum impedance and thus rejects them. Placing the tank in the shunt position reverses the filtering action. The tank offers minimum opposition to frequencies around resonance, thus does not develop a suitable output voltage. The band of frequencies right around resonance is rejected. At all other frequencies, though, tank impedance is maximum. Thus, output voltage is developed. All frequencies off resonance are passed. That pretty well sums up what we covered in the first lesson on filters. Now, in this lesson, we'll see how a parallel tank circuit can be used in filter circuits. We'll also discuss several other filter configurations. But in each case, we'll find that all the principles we developed in the first lesson still apply to these more complex filters. So let's first determine how a parallel tank circuit can be used to provide filtering action. Remember, there are two basic positions for component placement in a filter circuit: the series position and the shunt position. Now we'll start by placing the parallel tank in the shunt position. Okay, we'll remove the series tank and replace that with the parallel tank. Okay. Now, since we only want to determine its effect on the input frequency, we'll use a resistor in the series position of the filter, because the resistor is not a frequency-sensitive component and it'll have no effect on the input frequency. Thus, any frequency effects we see in the output must be due to the action of the parallel tank circuit. Now, let's hook this up on our trainer and see what occurs. Now remember, we'll be using an oscilloscope, a little breadboard trainer, and a signal generator for our demonstrations, as we did in the earlier lesson. Remember that the input frequency taken from this signal generator is applied directly through these connectors up to this point on our little trainer. Now, through this direct connection, we can see the input frequency displayed on the A trace or the top trace of the oscilloscope. Now, this is the frequency directly from the trainer or from the signal generator, the top trace of the scope. The other lead here, the one in the middle, is used to provide a synchronization voltage or an external trigger for the sweep circuits of the oscilloscope. Now, down here, in this circuit here, is where we'll hook up our filter components. This is the series position, and here is the shunt position. Now notice, as is always the case, the output is taken across the shunt component and is displayed on the B trace, or the lower trace, of the oscilloscope. Note also that, as we did in the first lesson, everything is grounded together. All right, let's plug in the components now. First, I'll put in the inductor. Remember now, we're going to make a parallel tank circuit. So we'll put the inductor in here, just like that. Now, there's the inductor. In parallel with that, we'll hook the capacitor, just like that. Now, there's our parallel tank circuit. Now, we need a resistor to complete the circuit, and we'll use one of the resistors that we used in the first lesson, variable resistor, set to the correct resistance to operate the circuit. Now, just get it plugged in there now. Okay. Now, you can see that we do have an output from our circuit. Now, we're going through the resistor and the tank circuit to ground. Okay, now watch the output, or the signal on the lower trace, as I vary the input frequency. Now, you see what's happening? The parallel tank in the shunt position is causing this circuit to function as a band pass filter. These frequencies below resonance are being rejected. There's not enough output there to operate the load device. But frequencies right around resonance are being passed. We have about the same output as we have on the input. So these frequencies are being passed. Now, these frequencies above resonance, however, are also being rejected. So we have a band pass filter. Now, as is true of all other filters, reversing the position of the shunt and series components reverses the action of the filter. Let's see. Now, the parallel tank is in the series position. The capacitor here, and across it, or in parallel with it, the inductor. Tank in the series position. In the shunt position, you'll notice that we have our resistor. Now let's check the frequency response of this circuit. At low frequencies, I have maximum output from the filter. But right around resonance, the output drops off to practically nothing. We're rejecting these frequencies right around resonance. Frequencies above resonance are being passed. So the parallel tank in the series position causes the circuit to function as a band reject filter. It's rejecting a band of frequencies right around resonance, but passing all others. Actually, the parallel tank works just opposite to the series tank. Now, both these circuits function as band pass filters. A series tank circuit in the series position or a parallel tank circuit in the shunt position serves to pass a band of frequencies around resonance, reject all others. So, why can't we combine the filtering components of the two circuits and make one band pass filter that has a series tank circuit in the series position, a parallel tank circuit in the shunt position? This circuit will still function as a band pass circuit, plus the filtering action will be improved because now there are two tanks to provide filtering action. To frequencies around resonance, the series tank offers minimum impedance, thus will allow them to pass through. The parallel tank offers maximum impedance to these frequencies, thus will develop maximum output voltage. And since the output is taken across the tank, the output voltage will be maximum at these frequencies. So the circuit has passed a band of frequencies around resonance. To frequencies above and below resonance, the series tank offers maximum impedance, thus will block or reject those frequencies. The parallel tank impedance is minimum to frequencies off resonance, and no output voltage will be developed. The circuit is rejecting frequencies off resonance. Now here's the series tank in the series position. Inductor, capacitor in series. And the parallel tank in the shunt position. It's our parallel tank inductor, our parallel tank capacitor. Let's see how this combination affects our output signal. As you can see the circuit is functioning as a band-pass filter. Now notice the good attenuation of those frequencies off resonance and the sharp response of the filter at resonance. Now this is due to having two tanks providing the filtering action. As demonstrated in all other filters, reversing the series and shunt components reverses the filtering action. Watch. Now these components, the inductor and this capacitor, are hooked up as a parallel tank and they're in the series position, and this inductor and this capacitor is hooked up as a series tank and it's in the shunt position. Now the parallel tank is offering maximum impedance to frequencies close to resonance and rejecting them, and the series tank is offering minimum impedance to frequencies at resonance and is not developing an output voltage. The filter is now rejecting frequencies at and around resonance. At frequencies off resonance, the parallel tank impedance is minimum and passes these frequencies through. The series tank impedance is maximum and develops the output voltage. The circuit is passing frequencies off resonance. And note the extremely sharp response since we're now using two tank circuits. We've now demonstrated all of the so-called simple filters. Next, we'll discuss modifications that can be made to the basic L section that will improve the overall filtering action by adding additional filter components to the circuit. We'll start out with the basic L section low-pass filter. The inductor in the series position of this filter will pass low frequencies but reject high frequencies. The specific frequency range the filter will affect will depend, of course, on the size of the components. If the inductor is 10 henries and the capacitor is 0.01 microfarads and the output is hooked up to the scope, as in our demonstrations, the frequencies passed will be below 600 hertz. Those above that value will be rejected. Now, changing the value of any of the components in the circuit will cause the filter to affect a different range of frequencies. However, there are a number of modifications we can make to this circuit without changing total inductance or total capacitance. And if we don't change the total values of L and C, then the filter will still affect the same frequency range. For example, if we split this inductor into two equal parts and connect the parts together like this, have we changed total inductance? Now, each inductor equals 5 henries. And since inductors in series are added just like resistors in series, the total value of inductance is 5 plus 5, or a total of 10 henries inductance. We can even move one of the inductors over here on the output side of the filter, and we still won't change total inductance. It's still 10 henries, and thus this filter will still pass frequencies below 600 hertz, reject those above that value. This filter is an inductive input-output filter. This particular configuration is called the T section because it's shaped like the letter T. This filter has several advantages over the simple L section filter. One, it provides better overall filtering because there's a filter component in both series legs of the filter, both the input and the output. Another advantage is that with this configuration, it doesn't matter which side of the filter is hooked up to the input. The impedance is the same in either direction. And this is an important consideration in circuit design. After all, this filter must be connected between two other circuits, and impedance matching between those two circuits is an important consideration. What it all boils down to is simply this: the filter configuration will be selected that best meets the requirements of the equipment in which it's to be used. In some cases, the simple L section will suffice. Other circuits may require a capacitive input-output filter. That too can be constructed from the basic L-section filter following the rule we established earlier. That is, once the total capacitance has been determined that will affect the particular frequency range we wish to filter, we cannot deviate from that total value of capacitance. Well, since capacitors in parallel are added like resistors in series, we can replace this 0.01 microfarad capacitor with two 0.005 microfarad capacitors in parallel. The total capacitance is still equal to 0.01 microfarads, so the circuit will still affect the same frequency range. We can even move one of the capacitors to the input side of the filter without changing total circuit capacitance. It's still 0.01 microfarads. This configuration is called the pi section filter because it's shaped like the Greek letter pi. It has the same advantages of the T section, that is, better filtering and impedance matching between input and output. However, this offers capacitive input, where the T offered inductive input. Again, the choice of filter is based on circuit requirements. This same logic can be applied to all the basic L-section filters. For example, let's consider the L-section high-pass filter. To construct a T-section filter with the same frequency response as this basic L-section, we must use two capacitors in series. Since capacitors in series are added like resistors in parallel, each capacitor must equal twice the value of this single capacitor. So, 2 times C here on the input and 2 times C here on the output. Total capacitance is still the same as in our original configuration. This pi section version of the high-pass filter shows that we have two inductors, two parallel inductors. Since inductors in parallel are added like resistors in parallel, we must have twice the original value of inductance in each of our legs of the filter. The advantages of the T and pi section version of the low-pass filter apply equally to the high-pass versions and also to the band-pass and band-reject filters as well. Let's first consider how we can improve the filtering action in our band-pass filters. This L-section band-pass filter can be configured as a T-section following the rules established earlier concerning total circuit inductance and capacitance. We'll need another inductor in series, and inductors in series add just like resistors in series. So 1/2 the total inductance must go in the input tank, 1/2 in the output tank. Capacitors in series are added like resistors in parallel. So to maintain the total required value of capacitance, we must put twice the capacitance in this tank and twice C in this tank. Thus, total values of L and C remain the same as originally required, and this circuit, the T-section band-pass filter, will still affect the same frequency range as did the basic L-section. Note again that the input and output impedances are equal, and since we have more filter components, our filtering action is improved over the basic L-section. The pi section band-pass filter can be constructed by, again, maintaining total circuit inductance and capacitance values the same as in this basic L section. We'll add an additional shunt leg to the basic L section like this. We now have two capacitors in parallel, so each capacitor must equal 1/2 the original capacitance. 1/2 here and 1/2 here. Two inductors in parallel, however, means that each inductor must equal twice the total value required. So 2 times L goes here in this tank, and 2 times L goes here. Again, total values of L and C have been maintained. And finally, we come to the band reject filter. It can also be reconfigured into a T or pi section. The basic L section band reject filter uses a parallel tank in the series position. To form a T-section band reject filter will require 2 parallel tanks in the series position. Notice how total circuit inductance and capacitance are maintained by placing half the series inductance in each tank and twice the series capacitance in each tank. The pi-section band reject filter has 2 shunt legs. Each leg has a series tank with twice the total shunt inductance in each tank and half the total shunt capacitance in each tank. Again, this is done to maintain total shunt inductance and capacitance at the required values. Now we have our demo hooked up as a simple L-section band reject filter, a parallel tank in the series position, our little shorting wire, and a series tank in the shunt position composed of this capacitor in series with this inductor, and of course the other side of the inductor going to ground. And our output is taken across our shunt component. Now we've said that the T and pi section filters provide improved filtering action over the simple L section. What do we mean by improved filtering action? Just this. This L section band reject filter rejects a band of frequencies from about 500 hertz up to about 700 hertz. Now since the specific frequency we want to reject is 600 hertz, this circuit is not too precise, is it? So let's make a T section from this basic L section and see if we can improve the frequency response. Now to make the T section, we'll need another parallel tank in the output leg of the series position, and we'll need to move our series tank over to the junction between the 2 parallel tanks. Now let's do this. Okay, parallel tank here in the input series leg of the filter and a parallel tank in the output series leg of the filter. And our series tank now is connected from the junction of these 2 tanks down through the capacitor, the inductor in series, and down to ground. So we have a T-section band reject filter. Now let's check the frequency response of this circuit and see if we have indeed improved it. All right. Notice now that I only have to go down to about 550 hertz, and I have maximum output from the filter. The same is true on the other side of the frequency we wish to reject. At about 650 hertz, I now have maximum output from the filter. So I'm now rejecting a band of frequencies much closer to 600 hertz. I have indeed improved the frequency response of the filter. This is true of all the more complex filters. The additional filter components serve to improve the frequency response of the filter, to cause it to do more precisely what we want it to do. Well, that's it. You've now seen all the basic filter configurations and how they can be modified with additional components to form T-section and pi-section filters. Your classroom instructor will show you a page in your study guide which shows all of these filter configurations. As you study them, keep in mind the basic principles we've established concerning filter circuits and how they work. Later on, when you study receivers, transmitters, antenna systems, and other advanced circuits, you'll see these filters again. What you learn now will prepare you for those later studies.
This arc is being created by 2 charged bodies. One is a positive charge, the other a negative charge. In this case, the force is great enough to cause electrons to leave the negative charge, travel through air, which is an insulator, to the positive charge. We've also found that a battery has 2 charged materials. If a connection is made between them, electrons will leave the negative charge and travel to the positive charge. Well, let me make such a connection. And you see the results. Though the pressure is small, it caused enough electrons to flow to burn the wire up. Now, this force is called an electromotive force, or an EMF. It's electromotive because it motivates electrons to move. Now, other terms used to identify the force is electrical pressure, difference of potential, but you'll probably see this one used most often, voltage. Now, regardless of the term used to identify the force, the unit of measure is identified as volts. Now, I'm sure you've heard the expression, a 6-volt battery or 110-volt outlet. Well, in this discussion, we're going to see some of the common ways of producing an EMF, or voltage. Now, keep in mind that the basic requirement is to develop two charges, one positive, the other negative. Now, one method of developing a voltage is by chemical action. I'm going to build a chemical source by using a piece of zinc, carbon, and sal ammoniac powder, a chemical made up of chlorine and ammonia. Now, I'll mix water in the sal ammoniac so that it's in a paste form. Now, by mixing water in, it should activate the chemical, make it more active. Mix it up real good. Now I'll put in the zinc here and the carbon here. Now here's what will take place. The sal ammoniac will react with the two materials and cause the zinc to gain electrons, the carbon to lose electrons. The zinc then will become negative, the carbon positive. Now an EMF or voltage will exist between the two. Now to check the results, I'm going to use this meter. Now, if a voltage or EMF does exist, it'll force electrons through this meter, causing it to deflect. So let's connect the meter to the material. One side here to the zinc, the other side here to the carbon. And of course, you can see that the meter does deflect. Well, actually, this is a crude form of dry cell battery. The two rods are called electrodes or terminals. The chemical is called an electrolyte. Well, a flashlight battery is an example of producing a voltage by chemical means. Now, by taking a look at a cutaway view, we can see essentially the same elements as the battery I just built. Now, the center post is a carbon rod. It develops the positive charge. The battery case is zinc. It develops the negative charge. The electrolyte is basically sal ammoniac powder, and it's packed between the carbon and the zinc. Now, this type battery develops an EMF or a voltage of about 1.6 volts. Here's another example of developing a voltage by chemical means. Its makeup is about the same as the flashlight battery. Taking a look at it, we see a carbon rod in the center, a zinc case, and a sal ammoniac electrolyte. Now, this battery also supplies 1.6 volts. In other words, the carbon-zinc combination generates 1.6 volts, regardless of the size. The chemical combination determines the amount of voltage. A car battery is another example of developing the voltage by chemical means. In this case, the electrolyte is sulfuric acid diluted with water. The electrodes are sponge lead here and lead dioxide here with a separator in between. Now, basically, this battery develops voltage in the same manner as the dry cell. The chemical reaction will cause the lead dioxide to become positive and the sponge lead negative, so voltage will exist between the two. One cell of this battery develops about 2.2 volts. So to furnish the voltage required in most cars, 6 cells are arranged to develop an output of about 13.2 volts. Checking the cell arrangement, we would have about 2, 4, 6, 8, 10, 12. The ordinary 12-volt car battery. Now, as you've probably realized, the chemical method is an effective way of producing an EMF or voltage. Another popular way is by mechanical means, commonly called the induction or generator method. In this method, all that's required is a magnetic field, a conductor, and motion between the two. Now, a magnetic field is similar to the field around a charged body. We can get an idea of how this field exists by using iron filings and a magnet. I'll sprinkle some filings on the glass covering this magnet. Notice how the filings form into lines, indicating the shape of the magnetic field. Well, when a magnetic field is brought near a conductor, it will force the free electrons of the conductor to move toward one end. The end that gains electrons will be negative, the end that loses electrons positive. Since charges are developed in the conductor, a voltage must exist across it. Let's demonstrate this method. Now remember, we need a magnetic field, a conductor, and motion between the two. Well, here's a magnet. It'll give us the magnetic field. This coil of wire, insulated wire, is a conductor. To check for a voltage, I'll connect the conductor across the meter. One side and the other end of the wire. Now, when I start moving the conductor, notice that the meter indicates a voltage. Now, it doesn't make any difference how the motion is attained. The magnetic field or the conductor could be moved. I've elected to move the conductor. The important thing is there must be movement between the two, or relative motion. Now, notice that the meter needle swings back and forth as the conductor is moved. This is because the field will force electrons to one end of the conductor and then to the other end. The result is an alternating or AC voltage. Now, you'll talk about AC in detail later on. For now, you should realize that it is different from that voltage we developed by the chemical method. Now, why do we say voltage is produced by mechanical means? Well, to obtain the motion, I had to mechanically move the conductor. Generators and alternators use this principle to develop a voltage, and the motion is usually developed by rotating the conductor. A voltage can also be produced by applying heat to certain materials. For example, if I connect this device to the meter and apply heat, we should get an indication of voltage. Let's try. Applying heat to the device, notice that as it heats up, the meter indicates a voltage. The more I heat it, the more voltage. Now, if I take the heat away and let it cool off, the needle slowly moves back. Now, if I help cool it off so that it's at normal room temperature, no voltage will be produced. Let's try it again. Applying heat, we get an indication of voltage. Now, a device that develops voltage in this manner is called a thermocouple. This illustration shows how the voltage is produced. When two dissimilar metals are brought into physical contact and heat is applied to the junction, free electrons will move from the more dense to the less dense material. The result is a deficiency of electrons in one material and an excess in the other. One material has developed a positive charge, the other a negative charge. Therefore, a voltage exists across the two. Now, of course, the amount of voltage produced by this method is limited, but due to its sensitivity to temperature changes, it's often used for temperature measurement and in temperature-controlled devices. A method similar to the thermocouple utilizes light rather than heat to produce a voltage. Now, devices in this category are made up of metals sensitive to light energy. When light strikes the device, electrons in the sensitive metal will become free and will travel to the film. The film gains electrons, therefore it's a negative charge. The metal lost electrons, so it has a positive charge. Charges have been developed, so a voltage exists across the two materials. Well, this method of producing a voltage is the photoelectric effect. And some of the devices that use it are photocells and solar cells. This is an example of a photoelectric device, a small solar cell. Now, by connecting this device to the meter, we should be able to see that the only requirement for developing a voltage is light. Let's try it and see. Connecting it across the meter, I'll use this lamp as the light source. Now, watch what happens as soon as I turn the switch on. The meter indicates a voltage. Then this little device produces a voltage simply by using light. Now, if I bring the device closer to the light, notice that the amount of voltage increases. More light, more voltage. Quite an amazing little device. Now, some uses of the photoelectric effect are to indicate light intensity, as in this light meter, and the solar batteries used to supply voltage in some space vehicles. Another amazing little device is this one, a crystal. It employs still another principle to develop a voltage, the piezoelectric effect. Now, the piezoelectric effect is this. Some crystalline materials possess the characteristic that if stress is placed on them, they produce a voltage. And the reverse of this principle is also true. That is, if a voltage is applied to the crystal, it will produce stress. This simply means that the crystal will vibrate or oscillate. It's difficult to show this method practically without advanced equipment. To apply enough stress to this to cause it to develop a voltage large enough to measure is impossible without breaking the crystal. However, later in the course, when you come to understand a few more principles, we will apply a voltage and check for an output from the crystal. Now, some microphones and some phonograph needles employ this technique to develop a voltage. Okay, we've developed a voltage by using a chemical, with mechanical energy, by applying heat, with light, and we discussed the piezoelectric effect. In each method, voltage is produced by creating a positive and a negative charge. Now remember, these are some of the terms used to describe this force. We said that voltage is the one that we'll see most often, and that we'll be referring to volts. Now, as you progress in your training, you'll see examples of how each method is used in actual circuits. Now, a little bit later on, we'll come back and see the relationship of this voltage to electron flow. I'll see you at that time.
To fulfill their missions, modern Air Force installations require an adequate and reliable source of electric power. This electric power, through an intricate network of wiring installations, provides lighting and power for a variety of requirements. The maintenance of these wiring installations is important not only to provide for uninterrupted operation, but because of the fire and electric hazards that result from defective wiring and equipment. In almost any electrical system that is in use over a long period of time, some malfunction will appear. To prevent possible damage to equipment, unnecessary work, and loss of man-hours,
analyzing and correcting the trouble must follow a planned, logical approach. A thorough knowledge of effective troubleshooting procedures will help you locate the trouble quickly, correct it, and restore the electric circuit to a safe condition. A comprehensive knowledge of troubleshooting techniques is valuable wherever electric power is in use. In wiring new construction, troubleshooting techniques are invaluable for checking out the circuits as they are installed, thus assuring safe, trouble-free service. Whenever repair work is necessary, the same techniques permit the electrician to quickly identify the circuits that require modification and allow him to proceed with confidence. And of course, in maintenance work, correct troubleshooting techniques are the key to rapid diagnosis of circuit problems. Trouble in an electrical system will generally be one of three types: short circuits, grounded circuits, or open circuits. One must be able to recognize the different types of trouble and identify each one. An electric circuit is a path or a group of interconnected paths capable of carrying electric currents. An electric circuit exists when a source of power is attached through a pair of conductors to an electrical device, such as a lamp. Current flows from the power source through the conductors to the electrical device. To provide a measure of control, a switch is normally added to turn the circuit off and on. To protect the circuit from damage in the event of trouble, a fuse or circuit breaker is added to the circuit. Let's take this basic circuit, enclose it properly in protective boxes and conduit, and use it to demonstrate the three most common types of circuit trouble. First, we'll examine a short circuit. A short circuit results when two bare conductors are permitted to come into contact with each other. The current no longer flows through the entire circuit. It is shunted directly from the hot conductor to the neutral conductor. When this occurs, there is only a very small amount of resistance in the circuit. According to Ohm's law, for a constant voltage, when the resistance is lowered, the flow of current goes up. This increase in current can cause heating of the wires and is the cause of many electrical fires. However, since the circuit is properly protected, the fuse or circuit breaker reacts to the excessive current and blows or trips, stopping the current flow. To correct the short, the damaged wires must be separated and, in most cases, replaced. Then, replacing the fuse or resetting the circuit breaker restores the circuit to normal operation. Now let's examine a grounded circuit. In any electrical installation, it is standard safety practice to connect the neutral conductor to the metallic structure of the power panel. In this way, the protective covering over the entire circuit, the conduit system, has the same potential as the neutral conductor. A grounded circuit results when the hot conductor is permitted to come into contact with some metallic part of the wiring system. Since the metallic parts of the wiring system are at ground potential, the current flow is shunted through the metallic structure to ground. Since the resistance of the circuit is lowered to an extremely low value, the current flow is increased until the protective device in the power panel reacts to stop the current flow. To correct this condition, it is necessary to locate the undesired grounding of the hot conductor and remove it. Then, when the protective device is reset or replaced, the circuit is restored to service. An open circuit results when one or more conductors in a circuit become broken burned, or otherwise separated to interrupt their continuity. An open circuit prevents any flow of current in the circuit. In this example, the neutral conductor has been broken to stop the current flow. If the hot conductor was broken instead, the effect on the circuit would be the same. If any part of this circuit fails, it breaks the continuity and stops the flow of current. Replacing the defective circuit component or repairing the broken wire restores the circuit to normal operation. The fuse or circuit breaker normally does not react to an open circuit. In the field, electric circuits are generally installed in a manner that rules out a visual inspection of the wiring itself. However, to be able to correct any trouble, the electrician must be able to identify the type of malfunction that exists in the line. The correct tools and equipment will make this identification easier. The tools normally used for troubleshooting are a voltage tester and a multimeter or buzzer-type continuity tester. We will demonstrate the use of these tools to troubleshoot this familiar basic circuit. The protective device has been set off, indicating that the fault is probably a short circuit or a grounded circuit. To check the wiring safely, disconnect the conductors from the power panel. For the hot conductor, this is normally done by removing the fuse or opening the circuit breaker. However, if more than one circuit is controlled by the fuse or breaker, the conductors must be physically removed from the power connection and separated. Since a short or ground is suspected, remove the other elements of the circuit by opening the switch and removing the bulb. To check for the suspected condition, use either the buzzer-type continuity checker or the ohm meter portion of the multimeter. When the meter is applied to one of the conductors and the metallic cover of the fuse box, it gives a high resistance reading, which means there is no continuity. Next, the meter is applied to the other conductor and the ground point. As it indicates no continuity, neither conductor is grounded, eliminating this as the source of trouble. When the meter leads are placed across the two conductors, the meter registers very low resistance, indicating that the two conductors are in contact with each other, a short circuit. Since the switch is open, the circuit problem must be in the length of conduit from the power source to the switch. To verify this, move the meter to the connections at the switch and check with the meter on both sides of the switch. On this side of the switch, the circuit indicates high resistance or no continuity. But on this side, the meter indicates the short. So the trouble has been identified and located. The short circuit is removed, and the circuit is checked once again with the ohm meter. This time, the circuit checks out properly. So it is now safe to replace the fuse, and the circuit is placed back in service. This time, let's examine another case where we come on the trouble site to find a blown fuse. Once again, to deal with the circuit safely, remove the wires from the power source. Remove the other elements in the circuit by opening the switch and removing the bulb. This time, instead of using a multimeter, let's use a buzzer-type continuity tester. This tester is simply a small door buzzer and a dry cell battery. When the two test leads are brought together, the current activates the buzzer and it makes a sound. Thus, when the leads are placed on a circuit under test, no sound means no continuity, while this sound means continuity. First, checking between the two conductors indicates that there is no short circuit in the first section of the circuit. And there is no continuity between the hot conductor and ground in this section. However, between the hot conductor and ground in the second section, there is continuity. Since this is the last section, the testing is complete. In a longer circuit, the diagnosis would be confirmed by checking the next connection. The ground is removed, and the circuit is retested at the trouble point, and all connections are restored. The light and fuse are replaced, and when the switch is turned on, the circuit is back in service. Perhaps the most common trouble in wiring circuits is an open circuit. In lighting circuits, the most common fault is a burned-out bulb. But sometimes the trouble may be caused by a loose or broken wire, requiring troubleshooting to locate it. Since the fuse did not blow, we suspect that the problem is an open circuit. Inspection or replacement of the light bulb reveals that it is good. The voltage tester will be valuable for this test. Checking at the source, there is voltage at the fuse box. Moving to the switch box, voltage is still present. Checking at the far side of the switch reveals voltage, so the switch is good. The final checkpoint is at the fixture box. At this point, there is no voltage. The trouble has been traced to this section of conduit. However, continuing a step farther can determine which conductor is defective. A check between the hot conductor and ground indicates 110 volts, which proves that the hot conductor is continuous. So the open circuit must be in the neutral conductor. Replacing the defective section of neutral conductor restores the service. For simplicity, we've been working with a very basic circuit. In practice, circuits usually involve several junction boxes and one or more branch circuits, all fed by the same fuse or circuit breaker. However, the procedure for troubleshooting such circuits is the same. Beginning at the power source, isolate one section of the circuit at a time until the trouble is located. Trouble in electric circuits can be classified into three general types: short circuits, grounded circuits, and open circuits. But regardless of the type of trouble, it can be found rapidly and safely by following sound troubleshooting procedures. Make an operational check of the circuit. Conduct a thorough visual inspection. Study the schematic diagram if it is available. Analyze the information that has been obtained. Locate the actual position of the trouble. Perform the repair. If you master this planned, logical approach to troubleshooting electric circuits, you will prevent damage to equipment, save unnecessary labor, and prevent the loss of man-hours important to the missions of the United States Air Force.